I'm Jessica Bayless, and a lot of people have been asking me how to start programming with data-oriented design, so I'd like to talk about that today. And the first thing is that it's really helpful when you're learning to convert some code that you know is not data-oriented, that you know is object-oriented instead. And Unity actually has some really great examples of conversion. In order to convert, my favorite from this particular website is the Combat Bees, and that's converting to their data-oriented tech stack, or DOT. A side note, though, is that data-oriented design is not about the entity component system. And actually, I'm going to show an example today that has no ECS in it whatsoever, and it's a really, really simple example, much simpler than the examples that you can convert that were on the previous website. And I just want to say, the entity component system itself, it's basically the reason why DOD is not the entity component system is that ECS is actually more of a design pattern that works really well in data-oriented design in terms of solutions, where the entity is an ID, the components are data, and the systems are transformations on those data. And so basically, it works really well in DoD, but it is not equivalent to data-oriented design. And data-oriented design really has two main components. And the most important is that it's data-oriented and that software basically exists in order to input, transform, and then output data. And it's all about the data. And it also has an interesting holistic view of software development that really looks across the whole pipeline. And it involves hardware and actually tools like compilers as parts of the actual development, which I call a supply chain view. So supply chains are basically, you start out, from the raw commodity and then you go all the way to the distribution. So, in this particular example, wheat is the data that gets transformed into something like bread, for instance, and then it gets distributed to customers. Oh, that sounds somewhat similar to software, right? And so data-oriented design really embraces this whole concept. And so basically your computer, your hardware, and your compiler are part of that supply chain. So the data goes from input to transform to output as part of this supply chain. And because of the way that data-oriented design looks at it, when you're engineering software, why would you ignore significant parts of your supply chain? Because when you do, it tends to lead to slow and broken software that guzzles power and does other things that you probably don't want it to do. And that's also why data-oriented design is not optimization. So optimization is about finding the best solution, usually the quickest solution, potentially the solution that takes up the least amount of space. Data-oriented design tends to find better solutions because it actually considers the whole supply chain, which a lot of software development seems not to. And so things like cache, which is, if it's good for the cache, it's good for your soul. It considers all of that, and many data-oriented design solutions don't actually involve real optimization. And in fact, the problem discussed today, which is a really, really simple problem, does not involve optimization at all. So I just want to say, data-oriented design is not equivalent to ECS, and it's not equivalent to optimization. So if you're doing data-oriented design, you're not necessarily doing optimization. So the problem I'm going to look at is L system generation. The reason why I'm going to look at that is that, first of all, L systems are really useful. They can procedurally generate things, from roads to rivers to dungeons to plants. They're useful for that as well. And they're actually pretty simple in terms of their definition. So this is a definition, I believe it's off of Wikipedia. that an L system is recursive and consists of an alphabet of symbols, which can have both variables and constants in it, a starting symbol, and a set of production rules that define how the symbols actually change on successive iterations. So, and the reason why I wanted to look at this particular problem is that it's problematic in terms of the definition. And there are really two words that are in that previous slide that really cause problematic engineering solutions. And those are the word recursive, which recursive solutions a lot of times are actually bad solutions, and the word alphabet. So alphabet can also lead to poor engineering solutions because alphabet implies strings. So a first naive solution of this problem, it gets split down into, when you do an L system, it involves successive iterations, and so you can actually split that down into parsing the language to end up with the resulting string of the L system for the number of iterations, and then displaying that as a drawing. So it's kind of split into two pieces, and this, the naive solution, is actually the bad solution. However, it's only 348 lines of code, and that includes lots of spacing, lots of comments, and a whole other bunch of, stuff, in terms of, the actual solution. Note that, that's got debug statements for timing and things like that in order to look at the actual performance of it. The size is actually part of what makes it a really good demonstration to actually look at and to, look at the data-oriented design of it. All the code versions are up on that GitHub site, and I will actually put it in a link down at the bottom of the video as well. So the code for a parse, originally the naive solution, is a string builder in C#. So it's a simple Unity script. It's C#. It's a string builder that has a two-dimensional array of rules to strings. It's run for a certain number of iterations, and then it gets printed out how long that actually took in terms of milliseconds. And that parse, has two pieces to it. One is getting the actual rule from that array, which is what this is. The other one is actually going through the L system, the number of iterations, and doing the string replacement in there. This is the bad solution. So 7 iterations of this, and it took 783 milliseconds to run through this parse 7 times, which is pretty hideous. A note on the display is really horrible as well. The naive implementation actually uses line renderers, and I will talk about that later. So let's look at the things that are actually wrong with this code. First of all, there's an extra for loop in getting the rules. Why not just use a hash table to, string goes to rule, right? For the replacement. So that was the first thing that I changed. And it's actually pretty easy to add a hash table into it. And this is actually the first thing that most students, when they're given the code, actually fix as well, is that, they say, oh, X goes to this, F goes to this. And so you can actually change the get rule method slightly, add, a hash table or a dictionary if you prefer dictionaries, because they're really kind of the same thing. And then that's not really going to fix the overall problem with this, because it does reduce the time a little bit. It was originally 783 milliseconds. It's now 759 milliseconds. So it did reduce it, but that is not the main problem. Because this array, the original array, was really, it only had 2 rules in it, so the for loop was really quick. So it fixed a little bit of it, but not a lot. The actual problem and what's causing the maximum part of the time is string replacement. And the fact that I'm using these strings. So all of the string replacement happening, which is, here it's the dot replace in the string. This is basically moving an array all over the place, and it's causing horrible things. The next thing that I have to ask is, well, like I'm dealing with strings, replacing in the middle of a string, and why am I doing strings in the first place? Does it have to be strings? Because of course it said alphabet in the beginning, and a lot of L systems are actually defined in terms of actual letters like F and P and S, right? But it doesn't have to, because the initial definition said symbol. And so this is probably the most important data-oriented design principle that I wanted to bring up today. And that's that in order to do data-oriented design, you actually have to know about the data. So there's a whole bunch of stuff that you need to know about the data. For instance, because this is such a simple problem, my L system data is actually really, really simple. And I can talk about the range, the type, the frequency, the number of iterations, the number of elements that happen after a certain number of iterations, so on and so forth. And for this problem, the nature of the data is actually, it's a symbol. And if you think about it, a lot of problems, in reality, you might write them out as strings, but in reality, they're symbols. And symbols can be anything. They can be numbers. And of course, computers deal with numbers really well. So in this case, let's just make it a byte. In particular, if I look at the range of things, the range of symbols that I've seen in different L systems, and I've looked through various books that have L systems, 2D and 3D, and usually they don't have a lot of symbols. Like you're dealing with probably a maximum number of 10 symbols. And so a byte fits that just fine. In fact, I could probably compress it further, but it's probably not worth it for me to compress it further because this is a simple demonstration for students. So I can, potentially make this a byte. I can, basically look at the different symbols of, that I originally had, which was X and F and the brackets, and I can turn them into numbers. And then, like I give myself a comment so I can see which numbers they are. I make sure to test it. And that's actually pretty easy to do. And so it becomes just an array of numbers. And if I'm going to actually do a certain number of iterations to replace those numbers, so, for instance, the difficult one is the first rule where I replace the 0 with that whole long string of numbers that's in the first rule array. And so basically, in order to do that and not to keep replacing in the middle of an array, which is problematic, I basically use 2 arrays and I swap between them. So I fill one with the current iteration, I fill the next one on the next iteration, and then I swap back. And so I swap between the 2 of them, and the array grows as the number of iterations grow. Because the number of iterations for my particular application, because it's a demonstration for students where they get to type in the number of iterations, it's not set. And so this is what that looks like in code. I've got a couple of lists, which in C# are arrays, and they basically, they both are used, they swap between one and the other, and the swap is actually on the second page where I have to have temp and do the regular swap thing. The one thing to note here is that in C# clear actually does not change capacity, which is important, so I'm not regrowing the array every single time I'm doing this. And so once I do that, all of a sudden my time is much better. So I went from 783 milliseconds to 4 milliseconds because I'm no longer doing the string replacement, and I just changed it to a bunch of bytes. Interestingly enough, once I do that, since it's just a couple of arrays now, I don't need a hash table anymore because, you know, basically I can just do the replacement based on, you know, the rules, the array of rules, since they're all numbers which can be indices into an array. So I have a jagged array of rules that have what they go to in the jagged array. And if I take out the hash table, it goes down to 2 milliseconds. So I go from 783 milliseconds to 2 milliseconds. And so that's with parsing. And basically what I've done is I've considered that, you know, I want to transform my data. What is it about my data that's important? You know, what's the range of the data? And, you know, I've considered what the data is, and that has allowed me to make this solution much better. And so that is the core component of data-oriented design in terms of looking at the data. And you really have to do this, and it's very important to look at the performance of what you're doing so that you can see that your data is actually going where you think your data is going, because sometimes it's not. And sometimes your data is getting used a lot more than you think it is. So you actually have to look at performance, and you have to look at profiling in order to see a lot of this stuff. Well, let me go back to the display for just a short little moment, and that's that the display itself has a lot of issues. And, you know, this is just, you know, the code that does the stopwatch for the display. The display method itself is rather obnoxious. It's actually just a switch statement that creates a line renderer object for every single line that's in the L system. And so you can see on the screen, there's like new object, new object, new object, new object, new object. This is actually really, really bad. I'm not even going at 60 frames a second. So we get to another data-oriented design principle, which is to design for the most common case. And for L systems, the common case is not a single line. And line renderer assumes, because it creates an object for every line, that you're really only displaying one or a couple of lines. If you're displaying a couple of lines, like a line in the center of the screen that's marking off 2 parts of a territory, it's just fine. It's a single thing that's only going to be drawn once. However, if I'm drawing this like 20 or 30,000 times, it's going to cause a lot of issues because each one of those is a separate object. And note that for most applications, one line is not the default case. And so it's a design principle to design for the most common case. I went to fix this, and my first, so you hit Google search on this and you say, how do I fix drawing lots of lines? And it says, use OpenGL, at least some of the solutions do. That actually causes some problems because apparently when you use OpenGL render calls, it puts it into immediate mode, which means that it's redoing it every single frame, which is problematic because it drops the frame rate tremendously. So for a large number of vertices, this is really, really bad. So let's not do that. That was a failed fix. I did not save it. It's not on the repository. I'm forgetting that it happened. My second try was to use a mesh object and then just add every single line, the vertices for all the lines to the mesh object, draw them as a line. And that actually took my draw time down quite a bit. There was a problem with this particular implementation though, the initial way I did it, in that I was adding them too much. The arrays were getting reset way too much in the second try, so I had to have a third try where I removed all the extra array setting and I just set it at the end of the display method. And I said, okay, let's figure out what all of this data is. So again, I'm looking at it in that I need all the vertices and all the colors, and I need all of this to draw my data. But let's actually just set all the data first, and then let's send it. And you can actually, the Unity actually allows you to actually set the buffer data directly, and that's what I did on the third try. And that basically took me down to a display time of 20 milliseconds, which was much, much better because I started off at like several seconds. So that was good. And I wanted to bring up here that data-oriented design is not about just sticking data into arrays, because when you're considering data, a lot of times it looks like you're just, okay, we have a bunch of data, stick it into an array. We have another bunch of data, stick it into an array. In fact, the whole entity component system, stick data into arrays, which brings up the whole structure of arrays versus array of structures. Structure of arrays is, if you've got simple data that is similar to each other stuck in an array. Array of structures is usually, an array of objects. And so DOD is not just about this. Why it's not about sticking stuff into an array? The best way of laying out data depends on what the actual data is. So sometimes it's great just to take all those positions out and stuff them into an array. And that's great. And that's the perfect thing that you want. It might not be, depending on how you're actually transforming that data and what you're transforming that data in terms of all that's needed to transform that data. So especially if you're doing SIMD, you might need the data in a slightly different format. And so you actually have to look at the data to determine the format that you need it in order to best transform it. And the best data structure might not actually be a data structure at all. For instance, if you want to keep track of the number of quarters that somebody has in their pocket, it's probably a variable, right? So there are cases where you can just get rid of the data structure and just use, increments, for instance. And also note that for really complicated data, your best data structure might actually be, a structure of arrays of structures. If it's complicated and it's all getting used at the same time, so it all needs to be in cache at the same time, that may be what your application needs. And so it's really about looking at the data and looking at, what gets used or transformed at the same time. So it's not about just throw data into arrays. Note that when I changed all this and I committed it, I can now do up to 12 iterations of my problem. 12 iterations is actually quite big and causes a really bushy plant for the problem I was looking at. But it actually, works. Whereas before, with the previous version, it just didn't work at all. Because that was way too many. I think it was primarily because it was too many objects in terms of the line renderers to actually draw, because that's over 1 million of them. So in particular, note that the solutions I'm talking about, they're not perfect solutions. There are things that could potentially be done better. If I actually wanted to go through and optimize and I wanted to make it more general, for a broader population, and it wasn't just a simple, couple-hour demonstration that I'm going to throw to a bunch of students to understand what an L system is. So dynamically growing the arrays could be handled better. Because right now I'm just creating them and I'm allowing them to dynamically grow because the students get to type in the number of iterations. And so I don't know the size that these arrays need to be. But if I knew a little bit more about what size they should be, then I could certainly handle that better and I could pre-allocate everything up front. So also the display right now, because I wanted the displays to be very much tied to the individual L system so the students could immediately see what the rules were for a particular L system and not have to look through a whole bunch of rules and figure out which ones actually applied. So I actually separated a couple of different displays for a couple of different L systems, and they certainly could be in one generic function that did them all, because there are a lot of similar rules in L systems that so you could probably have one generic display function. It'd be fairly easy to do. Okay, so hopefully that has explained some of data-oriented design in terms of a couple of the guiding principles and how you look at the data and how, you know, sometimes the way the problem is described is not going to yield a good engineering solution. And thank you very much.